Okay, thank you very much. I'm sorry for this delay. We have some technical problems with the computer. So let's start with this plenary session. The first speaker is Stephen Barnett from the University of Glasgow, and he will talk on optical forces and exotic materials. So let's welcome the speaker.
Thank you. So let me first start by thanking Saeed and the other organizers for the opportunity to come to this lovely sunny place and to speak to you today about some of our work on a range of topics related to exotic materials. And I'll say in a minute what I mean by exotic materials, but first I should acknowledge the efforts of my co-workers, Rob Cameron, Jörg, Let's start again. These buttons are a bit close to each other. Rob Cameron, Jörg Goethe, Alison Yao, and Rodney Loudon. So by an exotic material, what I mean is materials that are a bit unusual for most of us working in optical physics, but are very familiar to people at this conference. I mean materials and objects for which the magnetic properties are every bit as important as the electrical properties. So not the familiar dielectrics that we spend most of our time working with. I'm going to break this down into 4 pieces. A general introduction about optical forces, a little bit about optical momentum, what happens to the momentum of light when it goes into a medium. There's a subtle problem more than 100 years old, and if you think about that for magnetic materials, it's more subtler still. And then a switch of tack from forces and momentum to something closer to angular momentum. I was talking about the helicity of light, and then what that does on chiral objects, and most specifically, molecules. So, optical forces, of course, have a long history. We're familiar very much with the many of the mechanical properties of light. It was Kepler, nearly 400 years ago, who suggested that the tails of comets were due to the radiation pressure, essentially the push of the light from the sun. And Maxwell, in his famous treatise, calculated essentially the force or the pressure on the surface of the Earth in rather delightful units. He talked in terms of pounds of weight, but when you do the conversion, it corresponds to a pressure of about 4 micropascals, and that's spot on. In the more modern domain, we're used to the idea of using lasers for trapping objects, and most specifically, due to the work of Art Ashkin and those who followed him, the idea of trapping a dielectric object, a sphere or even an atom, at the focus of a laser beam. And what's doing the trapping there is, oh dear, it's fallen off the bottom. It's a gradient force. So essentially the energy of the particle is attracted toward, or the particle is attracted towards strong fields by the gradient in the energy. So let me, in a more tutorial sense, step back and think about the force on an object. And the simplest object I can think of, simplest neutral object, is just a dipole. If I put a dipole in an electric field, so this is the center of mass of the dipole, here's the separation of the positive charge and the negative charges, and just stick this into the Lorentz force law, you find, of course, that the electric field pulls these 2 objects in different directions, and then due to the motion of these 2, you get a magnetic piece as well. And if I think of this as being a small dipole object, I can just do an expansion, a Taylor expansion of this field, and end up with the dot product of the dipole moment with the gradient of the electric field. So it sees the gradient of the electric field, and here's the magnetic piece due to the oscillation of the dipole. And if I simply add up all of the dipoles inside the medium, the sum of the dipoles becomes a polarization, and you end up with this form of the force. So the polarization and the gradient of the electric field, and then a piece due to the oscillation of the dipole. What about magnetic media? This has been a rather contentious topic, but there is in fact a very simple way to get from this form of the force on an electric dipole to the force on a magnetic medium, and that's to exploit a symmetry which is inherent in Maxwell's equations. So I've written Maxwell's equations in their form without free charges and free currents, and the symmetry which was spotted by these two guys, this is Heaviside, this is Joseph Larmor, was that you can rotate the electric field, so we can take a cosine of theta times the electric field plus sine theta of the magnetic field and replace my electric field by that. I can rotate, similarly, the magnetic field in the opposite sense, and likewise for the auxiliary fields, the D and the B, and then Maxwell's equations are unchanged. And that's a symmetry of the charge of the Maxwell's equations in the absence of free charges. And if you look at the quantities which we know and love, this is my energy density. Here are two candidates for the momentum density of the light, which I'll come to a bit later. These quantities are also unchanged by this transformation. And so simply by applying this reasoning, this symmetry, not just to the Maxwell equations and these quantities, but also to forces, you can get straight to the force on a magnetic medium. There's one subtlety which we have to take care of, and that is that it shouldn't be B sitting in here in the magnetic medium, but it should be H. And then if I apply the symmetry, I pick out pieces corresponding to, this is the electric dipole gradient, this is the magnetic dipole, and the gradient of the magnetic field, and here's the corresponding velocity piece, corresponding by P dot cross H. And this is exactly the form that, by more exotic methods and more rigorous methods, that Einstein and Lau broke down over a century ago. It's also what you would get if you picked up on this guy's work. This is Gilbert of Colchester, who was the first person to suggest that the explanation for magnetic fields was magnetic poles. And if you just apply exactly the same piece of reasoning, but thinking of a magnetic dipole as being a separated pair of magnetic poles, it's a fiction, of course, but if you think in that way, you get precisely to this formula. So what about forces on media? So I'm now thinking in terms of an object that has both an electric response and a magnetic response. And in order to make a sensible stab at this, our approach of Rodney Loudon and myself, was to think in terms of the force exerted by a single photon. Then we can think of a per photon analysis, if you like. And in order to do that, we have to quantize the field inside the medium. And as we all know, in the quantum theory inside a medium, you get an interaction between polaritons, both electric and magnetic, and the free field. And that gives us a structure where we have multiple branches, multiple polariton branches, so a number of different solutions of my dispersion relation, many different frequencies for each wavelength or each wave number. So this is a typical example, one in particular where, because this polariton branch sinks rather than grows with K, this corresponds to a negative refractive index. And I mention this because we have to be careful about including all of these polaritons. We can't have just a polariton which goes falling off like this corresponding to negative index. In fact, the form of these are constrained by causality by a number of sum rules. So for each of these curves, we can write down essentially a phase velocity, an omega over k, and a group velocity, a d omega by dk. And however we construct it, we have to satisfy these four sum rules. So that's just a cautionary tale. So because I'm interested in the force on media, one natural way to proceed about a force is to think in terms of the rate of change of a momentum, or what does the momentum look like inside the medium. And there's a subtlety associated with the momentum in a medium, which was also over 100 years old, and it's due to these two people. This is Minkowski and this is Abraham. And each of them, they had a rival form for the density of momentum inside a medium. So in free space, of course, it doesn't matter whether I think about E cross H or D cross B. They're the same. But inside a medium, because of the refractive index, these quantities are not equal to. And Minkowski would have us believe that the momentum density is the cross product of D and B, but Abraham would have us believe that it's the cross product of E and H. And the century-old argument is which one of these two is correct. So what I'd like to do is to take a few moments to show you that unambiguously it has to be this one. And then when I've shown you unambiguously that it has to be this one, I'll show you unambiguously it has to be that one. But first, just to emphasize the issue that there's a problem to a problem to address. This is just a very simple sketch analysis of the fact that these momenta are different and can be very different. So if we think about a simple scaling, this is my integration of my energy density corresponding to the energy of my photon. I can, of course, rewrite this in terms of a purely electrical piece and a purely magnetic piece. These two pieces are equal. And then that tells me how these fields have to scale for the individual photons. And then when I reconstruct my Minkowski momentum and my Abraham momentum, I find, well, actually, that's not very clear, that the momentum in free space, of course, is just h bar omega over c. The Minkowski momentum is this free space momentum multiplied by the refractive index, and the Abraham one, which is lost off the bottom, is the same free space momentum, but divided by the refractive index. Of course, we're familiar with materials which have refractive indices of the order of 10. That's not too much of a stretch. So these two momenta might differ from each other by 100. And so you'd think the question of which one is right would be absolutely trivial with such a huge distinction. It's not. So first of all, let me prove to you that the correct momentum is the Abraham momentum. There's a little calculation which you can do, a little back sketch of the envelope calculation. Let me think in terms of the center of mass energy. So it's a slight extension from the idea of the uniform motion of center of mass. Of course, in relativity, we know it's the energy which travels with uniform speed. So here's my photon. Here's a block of medium, transparent medium, mass m, and initially with zero momentum. The light goes into the medium, comes out of the other side, and while it's inside the glass, of course, it's moving more slowly. And that means that the block of glass has to have been in motion in this direction. Of course, it stops once the photon is left. And because of the finite speed, this photon is retarded compared to where it would have been if it hadn't gone through the glass. So you can work out how far this block of glass has had to move simply to make the motion of the center of energy uniform. And you find this simple relationship. Here's my shift in the position of the glass. Here's its energy. Here's the shift in the position of the photon. L is the thickness of the glass. That allows you to extract how far the block of glass has moved. And then that tells you what the momentum of the glass has to have been, because it's just the mass. This is the distance it's traveled, and this is how long it's had to move. And you find that it's the initial momentum of the photon minus this bit. So the rest of the momentum must have been taken up by the photon. Therefore, simple conservation of the center of mass tells us that that's the momentum of the photon, and that's the end of the story. So I hope you're all convinced. Oh, incidentally, if I tried to do the analysis with the Minkowski momentum, the block of glass would have moved in the wrong direction. So if you're convinced by that, let me show you that, in fact, that's not right. It's the Minkowski momentum that's correct. And here's a very simple idea based not on the, if you like, the particle nature of light, but the wave nature. We all know that if you put light through a slit, you get a diffraction pattern, and that we can estimate the width of this central fringe simply by looking at essentially the uncertainty principle. So because this slit has a finite width, I introduce a spread of momentum in this direction, this px. And that's simply, well, here's my momentum in the forward direction, my pz. Here's my h bar divided by delta x, and that gives me my slit width. If I do the same analysis, in fact, indeed the same experiment with a medium in here, what I find is that the width of this central peak narrows, and it narrows by the refractive index. So this is narrower than this peak by this factor of n. Exactly the same analysis goes through. There's only the frequency of the light and universal constants plus the width of the slit in here. And so if this opening angle is reduced by the refractive index, my momentum has to have been increased by n. So that's a demonstration that is, in fact, multiplication by n, not division. And therein lies 100 years of argument and debate. If you want to think in terms of single photons, there's another way of seeing it as well, and that is simply that the de Broglie relationship tells me that the momentum of a particle is Planck's constant divided by lambda, and we know that when light moves into a medium, the refractive index modifies the wavelength, so it's reduced by lambda, and that tells me simply that the momentum must increase. So it's also a consequence of the de Broglie relationship. So what's going on what's going on is that the simple resolution of this puzzle is that light carries not one momentum, but two. And we recognize in quantum mechanics of charged particles and other interacting objects that there is a momentum which is the mr dot, and there's a momentum which is p, the h over lambda. This is the canonical momentum that sits in the commutation relations. This is the kinetic momentum familiar from Newton. And they're related to each other. They're not the same. They're related by this relationship. There's a dipole moment across the magnetic field, and there's also, for magnetic dipoles, a corresponding m cross E piece. And if I look at my Minkowski momentum in the presence of this medium, I can write this in terms of E cross H, and then there's the P piece which modifies D, and the E cross M. And these two bits are precisely these contributions. So if I sum over all the dipoles forming the medium, I come to the conclusion that this object, the Minkowski momentum, is the canonical momentum of light, and the Abraham one is the kinetic momentum. So it's an uncomfortable thing, but we have to cope with two momenta. The resolution of the puzzle is that they are both correct. So what about if I think in terms of, I mentioned this idea of putting light into a medium. So let's think in terms of what happens if I have a single photon coming into a piece of dielectric. Well, of course, what happens is that at the front face, the photon can be reflected or it can be transmitted. And I know about my reflection and transmission coefficients, so I can work out the momentum inside. So that's the incoming momentum, h bar omega over c. On average, this is the momentum. It's in the opposite direction because it's reflected, and this is simply my reflection probability. And balancing out the momenta, this gives me a transmission coefficient times the momentum of the photon. And if I do my maths right, I find that the global momentum conservation simply tells me the momentum of the photon is, well, this is rather peculiar. It looks like the average of the Minkowski and the Abraham momenta. So it's 1/2 of multiplying by the refractive index and dividing by the refractive index. This gives us an interesting puzzle because the fact that I've got my refractive index in here provides an interesting question for those interested in negative index materials. Because if the refractive index is negative, this tends to suggest that this momentum is pointing in the wrong direction. And that's essentially what got us, my colleagues and I, interested in the question of negative index materials. It turns out to be not true. What you find if you have a magnetic medium, of course, you've got to go back to square one and do the analysis more carefully. And what we find is that we get the average of, and now a modification which is the average of multiplying by the impedance and 1 over the impedance, which replaces our refractive index. And of course, these quantities are both positive in my negative index medium. Notice also that the entire basis of this was putting together a theory which satisfies this electric magnetic symmetry. So if I interchange the roles of the electric and the magnetic field, I shouldn't see any change, and that's very satisfactory here, of course, because if I interchange my electric and magnetic fields, the epsilon becomes a mu and the mu becomes an epsilon. So this quantity satisfies that symmetry, which is most satisfactory. So let me switch tack now and think about helicity for a moment, and now we're thinking about its effects on magnetic media, which are going to be chiral molecules. So helicity is a phenomenon which has been discovered and rediscovered in a number of different fields of physics. The particle physicists think in terms of the helicity of a particle as being the projection of the spin along the momentum divided by the momentum. So you see in the particle physics textbooks, this is the definition which we have for the helicity. It also appears in fluid mechanics associated with rotational motion in the fluid. And there it's a volume integral of, this is the dot product of the local velocity with the curl of the velocity. And in plasma physics, it's associated with closed lines of helicity, which are mapped out in terms of the dot product of the vector potential with the magnetic field, which has the same idea, it's the same origin as in fluid mechanics. It's the dot product of the vector potential with the curl of the vector potential. For light, we have to be a little bit more subtle, because the principle is again this idea of keeping a symmetry between the electric and the magnetic fields. So here, this is a promising candidate for the helicity of the light, but it fails in the sense that only the vector potential and the magnetic field appear. There's no electric part. So the way to fix that is to introduce a second potential, which is, so the vector potential is related to the electric field through a time derivative. The magnetic field is the curl. With our second potential, we look at it the other way around. So we have a second potential, the curl of which is essentially our electric field, and the time derivative of which is our magnetic field. And that means we can symmetrize our helicity with both the magnetic piece A dot B from plasma physics and an electric field piece as well. And very satisfactorily, if I integrate this object out and calculate it for a quantized field, without any approximations, this turns out to be h bar multiplied by the number of left circularly polarized photons minus the number of right circularly polarized photons. So it has the right property for a helicity. It also corresponds, it's a conserved quantity, it corresponds to a symmetry, and the symmetry is precisely this electric magnetic symmetry. So the transformation which is generated by this conserved quantity is simply a rotation for each plane wave about the direction of the propagation of that wave. So it takes the magnetic field and the electric fields and rotates them in this sense. And of course, that's still a satisfactory field, still a satisfactory solution of Maxwell's equations, but it's one which has had this Heaviside-Larmor transformation implemented on it. Now, one thing that's very important, and it's crucially important for seeing why helicity matters for chiral objects, is that helicity is not spin. This quantity is essentially, well, this quantity is a scalar, or more precisely a pseudo-scalar. It doesn't have a direction. So it's a sum of it's the difference in the number of left and right circularly polarized photons times an angular momentum, but the directions is along the direction of propagation. So this quantity doesn't have a direction, but spin, of course, does. So spin is the same quantity, but now it's this angular momentum mapped onto the direction of propagation for each of these modes. So this quantity is a pseudo-scalar, this one is a pseudo-vector. Why pseudo? Because of what happens to these objects, these quantities, when you look at them in a mirror. So if you think about it, if I have a circularly polarized beam coming into a mirror and being reflected, so the angular momentum is conserved, so that means that when the direction is changed, the spin doesn't change, but the helicity does. So that the handedness of the reflected light is opposite to what went in. And there's another connection between these objects, between the spin angular momentum and the density of the helicity. They satisfy a continuity equation, which is essentially the analog of the Poynting's theorem. So I can think in terms of this as being a locally conserved density in much the same way as the energy is conserved, and this is the spin is the flux or the flow of this helicity in much the same way that my Poynting vector is the flow of energy. So that's another illustration of the relationship and yet distinction between helicity and spin. So why did I bring up helicity in the context of exotic materials? Well, entirely because of its relationship with chirality. So we all know about chiral objects. There's some confusion about exactly what chirality is, but for me, it's precisely the distinction between the two hands, the left and right hand. And in fact, this is the way that Lord Kelvin in 1894 introduced the notion of chirality. He says, I call any geometrical figure or group of points chiral and say that it has chirality if its image in a plane mirror, ideally realized, cannot be brought into coincidence with itself. So the idea is that the object and its mirror image are distinct. And this is crucially important in chemistry, and particularly in organic chemistry, because carbon is tetravalent. And so if I have a carbon in a molecule, it can be attached to 4 distinct groups, 4 distinct elements. And as soon as I have this structure, I have a chiral object, a chiral molecule, because this molecule and its mirror image are distinct. And you can see that if I try to rotate this object into itself, I can match up two, but the other two objects are going to be in the wrong place. So in order to make these two molecules the same, I have to do a rotation, but I also have to interchange two groups. So that these two are then a chiral. Now this is extremely important in the life sciences, and just by way of amusement, let me give you some examples. These are not very accurate, I'm afraid, or not very informative sketches of rather simple molecules. I think all you have to pick out of here is that they're not very big. There's not a lot of atoms in them. But in each of these molecules, there is one carbon atom which has this feature of being attached to 4 different groups. And the distinction, in fact, between the left-handed version and the right-handed version is the position of one hydrogen atom. So you flip one hydrogen atom over and one turns into the other one. And yet, nevertheless, these objects have very distinct behaviors. So this molecule is carbone. It exists both in both of these versions, both of these enantiomers exist naturally in the world. This one corresponds to or gives us the flavor of spearmint. This one is an ingredient in a proprietary decongestant, a cold remedy, and this one is, as far as we can tell, biologically inert. If you flip the hydrogen atom over, you change your flavor from spearmint to caraway, so caraway seeds in a mirror taste like spearmint. This one turns into an illegal narcotic, which is crystal meth, and this one into a rather effective herbicide. And there are many, many, many more of these. In fact, this is also big business. I've updated these figures slightly. I think this estimate must be about right. The net worth to date of unichiral pharmaceuticals is of the order of 3 times 10 to the 11 US dollars. So that's the size of the business that is going on. So, what I'm going to describe now is at least an idea for optical forces on chiral molecules which are chirally selective. So the basis of this is going to be this dipole force. So this is just to remind you, this is the force which is due to the gradient in the energy or the gradient in the square of the electric field, and then there'll be a parameter outside which is characteristic of the dipole response of the atom. If I have a molecule which is chiral, then it will exhibit not just an electric dipole moment, but a magnetic dipole moment. This is our favorite molecule, hexahelicene. It's essentially a bit like a twisted piece of graphene. And it exists in 2 different forms, a sort of left-hand staircase and a right-hand staircase. And I chose it because it's particularly simple to see why we have this relationship of electric and magnetic dipoles. So if I put an electric field across this molecule, the electrons will flow, can flow through this essentially graphene sheet, and they will flow either clockwise up the spiral or anti-clockwise up the spiral, depending on which of these 2 molecules we have. And because that's then a current loop, or a piece of a current loop, that means I'm also going to induce a magnetic field, so I get a magnetic dipole response. And you can see that the magnetic dipole moment will be anti-parallel to the electric dipole moment for one molecule and parallel for the other. And that's the handle that we have. If we can use the electric and the magnetic dipole moments, we have a way of distinguishing between these 2 molecules. And then what we find is that the force experienced by these 2, there's another parameter based on these electric and magnetic responses, but in this case it's the gradient not of the energy but of the helicity that gives us a force in the opposite directions. If we can get rid of this admittedly rather large electric dipole force, what's left is discriminatory, and it allows us to pull the 2 different types of molecules apart. Let me say a few words about how this works. This is just intended to be indicative. Why is it that I might expect these 2 different magnetic responses to give opposite directions of force? Well, the energy of interaction between the molecule and the light is just, this is our dipole interaction, d dot E, and of course there's also a magnetic piece, an m dot B. And because of this effect, if I have a time-varying electric field, an oscillating electric field, I generate a dipole, electric dipole separation, but also a current. And so my electric dipole response is proportional to the electric field, but also to the time derivative of the opposed magnetic field. And likewise, the magnetic dipole moment depends on the magnetic field and the time derivative of the electric field. I can rewrite this B dot in terms of omega squared times my C potential, and likewise my magnetic dipole omega squared times my electric potential. And then the energy, this is the normal dipole energy, but it has another piece which is proportional to the helicity. So the gradient of this quantity, which will be my force, contains this familiar electric dipole force, but also, it's fallen off the bottom, apologies, also this magnetic piece, this piece which is proportional to the gradient of the helicity. So in order to separate out these two different types of molecules, all I need is a helicity pattern, preferably with a flat intensity, in which the molecules will be naturally pulled apart by this force. Let me mention in particular this paper by Cyriac-Genet and his colleagues, who looked at not just this idea of separation on forces by forces, but also there's an analogous behavior for torques, which are allowing to twist the molecules in different directions as well. So here's the idea. Let me see if I can make a pattern of light which has got helicity fringes but a uniform intensity. Then I've got precisely what I need to separate out the molecules to produce forces in different directions. And in principle, at least, it's surprisingly straightforward. I need something like two different plane waves which are orthogonally polarized and propagating at an angle to each other. And then, because these two plane waves are orthogonally polarized, I get a uniform intensity distribution. There's no interference. But because of the relative phases between these two fields, these two polarizations will add up either to give me a linear polarization, a left circular polarization, an orthogonal linear polarization, a right circular polarization, and so on. And this is precisely a fringe or a fringe pattern in helicity. And so if I can make this kind of pattern of plane waves or something approaching it, I get regions where the helicity is positive, this is the darker version, and negative, oscillating in a sinusoidal fashion, and the gradient through this zero is going to pull the molecules either to the left or to the right. So something like this. This is near one of my nodes of my helicity pattern, pulling one enantiomer to the left, one enantiomer to the right. Now, this force is small. It's certainly small compared to the familiar electric dipole force, but our analysis with realistic figures suggests that it should be possible to separate out something with a big response like hexahelicine by perhaps plus or minus half a millimeter. So not exactly what you want for the mass production of pharmaceuticals, but as far as quality control is concerned, may be a useful laboratory technique. If we can cool our molecules and move into the de Broglie regime, so that was essentially more like a Newtonian forces, Stern-Gerlach regime. So if we can cool them down to make a reasonably coherent plane wave of these objects, then we get diffraction patterns. And the idea then is that here are my different diffraction orders, and we get a separation between the fact that we get a diffraction orders for our two different, for our chiral objects, but a non-chiral object doesn't see helicity at all and just goes straight through. I'll skip over that. If we can find a way of blazing this grating, and the simplest way to make this effect is simply to blot out every second one of these fringes, then in addition to the diffraction, we also get the fact that this form of hexahelicine twists only to the left, this version only to the right, and then we have separation in the diffraction orders due to the different enantiomers as well. Skip that too. Right, so let me just finish up with some conclusions. So the key point about that links up these exotic media and also the chiral molecules is the essential feature that we have to deal with both the electric and the magnetic response. And it's this old symmetry due to Heaviside and Larmor, this electric-magnetic symmetry of Maxwell's equations, that's been our guide, and also a consistency check. So in doing these rather complicated calculations, we have to make sure that we always respect this electric-magnetic symmetry. That symmetry also tells us what the correct form for the helicity of the light is, and we can use that, or starting to use that, as a tool for manipulating and analyzing chiral molecules, including those which are of significance biologically. And finally, let me, if you want to know some more about this work, let me advertise the papers by my colleagues Jörg, Alison, and Rob, which are to follow. Thank you all very much for your attention.
Okay, thank you very much. We have time for some questions.
When you define spin and the helicity, one is the pseudo-scalar and the other pseudo-vector. You define that. And I wonder what happens if you put the vortex, for example, this helical light, which has interangular momentum, then how you define this helicity and then spin, including, this angular momentum, including both spin and intrinsic angular momentum.
Ah, yes, okay. So, it's interesting. A complete characterization of the angular momentum of the light is the total angular momentum and the helicity. And the helicity is associated with the spin, but there isn't an analog of the helicity for the orbital angular momentum, which we're familiar with. And the reason actually is very simple. What we're doing is we're taking a projection along a direction of propagation for our plane waves. And in order to get the momentum contribution for the light, of course, as far as the angular momentum is concerned, is perpendicular to because it's the cross product of the radial distance with the angular momentum. So it's not the momentum contribution in the forward direction, which is important for the orbital angular momentum. Of course, it's this piece. And so there isn't actually an analog of the helicity for the orbital angular momentum.
Thank you. You use the formula for the energy, which assumes that the material has no dispersion. Of course, there's another term in there if there is dispersion. Does that change any of your arguments?
Yeah, absolutely. Oh, gosh. Yes, absolutely. You have to be far more careful. The calculation I presented here is just a sort of hand-waving, an order of magnitude sort of rough idea. Of course, dispersion is vitally important, and especially when you're talking about metamaterials, of course, as you know very well. Yes, is the answer to your question. It does become more subtle. It does become more important.
Same answer.
I beg your pardon?
Same answer. Get the same answer.
More or less. More or less.
We'll talk about it later.
You are talking about plane waves for chirality discrimination. What about near fields? Can we realize optical microscope for chirality discrimination?
Yes, is the simple answer. So there are a number of rival techniques. Certainly, The intense fields associated with evanescent fields could be made to be chiral, and these are also candidates for discriminating between the chiral molecules. So yes.
I think we still have time for another question. There are plenty of them, so let's give another chance. The other question. Okay, then let's thank the speaker, and let's go to the next one.